Hi, welcome to week 3 of social network analysis. This week we'll be tackling centrality. Centrality tells us which nodes are important in the network. This goes beyond just looking at social networks and which nodes might be popular, and to looking at all sorts of different networks, trade networks, who are the most important importers, exporters, nodes that bridge different regions and facilitate trade. In biological networks, which genes, for example, play a very crucial role in regulating entire systems and processes. In infrastructure networks, which nodes are critical, such that if you were to remove them, you would significantly impede the functioning of whatever the network is supposed to do. So identifying such important nodes is pretty critical, and it may be one of the first things you want to do when you look at a network is look at what nodes are most central. If you go to the website moviegalaxies.com, what you'll see are a bunch of networks that have been constructed out of the scripts. So they parse, I'm guessing automatically, through the scripts and see this character address this other character at this point in the movie script, so let's draw an edge. So if you look at, for example, the 1993 movie The Fugitive, you can see immediately that there's this central node here, Kimball, and this is Dr. Richard Kimball, who is the fugitive, falsely convicted of murdering his wife. And you see here a secondary important individual who is Deputy Gerard from the U.S. Marshal Service, who is pursuing Kimball throughout the movie. And this you can immediately infer without ever having seen them. Well, you can't infer all those details, but you can infer that both Kimball and Gerard are central actors. Similarly, if you look at Heat, you see a similar pattern where Detective Hannah is pursuing Neil, who's like a longtime crook, right? And you start to see these kinds of patterns. Now, of course, if the movie just has one central actor, for example, in Memento, there's just Leonard, and he's the most central. So even though he may not actually remember having all of these edges, all these interactions, because what happens is he keeps losing his memory, we can see, in fact, that over the course of the movie, he's the most central actor. The question is, though, is counting edges enough? So what I'm showing you here is a fragment of the network, my first social network that I ever gathered data for. And these were Stanford homepages. So take yourself back to 1999. This was before Friendster, before Facebook, before MySpace, really. People were still constructing social networks online in the best way that they knew how, which was to link their home pages together. And the way that I caught on to this was that, this was actually back in my undergrad days. A friend of mine had linked from her homepage to mine and said, "Hey, Wada, how come you're not linking back to me?" And so I started, actually, my homepage had a friend's page that linked to my friends. And once I was at Stanford and in grad school and starting to study networks, I grew curious, how many people actually did this. And so I gathered the data, and this is the my local network neighborhood in the Stanford homepages. I linked to Orkut Büyükoktin, who here looks very central. He is also linked to or links to many other friends, and in fact, he was sort of the center of my social universe in graduate school. Now, the complete picture, though, is something like this, right? So, sure, if you look at degree, Orkut may be one of the highest degree individuals in the network, but still you would probably say that he's peripheral to this whole network. However, that didn't last long because Orkut actually created Club Nexus, which was it had exactly the same functionality as Facebook, was created around the same time as Facebook, but was for Stanford students. And there he definitely was the center of the network. Then when he eventually started working for Google, he he created their first social networking service that was called Orku.com and was incredibly, successful there. So much so that, where that service flourished was especially in Brazil and in India. And so when he went to Brazil, he actually needed a security detail. He'd become so very central thanks to starting this hugely popular social network. But back to this picture, it tells us that back in 1999, when Orku was still a new grad student, maybe his close friends had come to appreciate him, but he was still not the center of the Stanford social life. So what kinds of centrality measures could we use in order to make that distinction? So there are many different notions of centrality. We talked about in degree and out degree before, and we'll review them, but there are also notions of betweenness, closeness, and we'll also talk about eigenvector centrality. So in degree is just the number of incoming edges that a node has, and here x has higher in degree than y happens to have in degree 0. I have here plotted the network of oil exports using the NBR United Nations trade data. In fact, I think they base the data on imports rather than exports, but you can because they consider them more reliable, but you can kind of symmetrize the two. And I use the category that corresponds to petroleum and petroleum products. And you can see this, every node is a country, and there's a directed edge from the exporter to the importer. So just to check your understanding, which countries have high in degree? That is, they import petroleum and petroleum products from many others. Now let's talk about out degree. Out degree is just the number of edges that emanate from a particular node. So here I have just modified the same network of oil trade, and I have sized the nodes by their exports, and I've also colored according to the ratio of exports to imports. So if that ratio is high, the node is more blue. If that ratio is low, the node is more red. So for example, here, the US imports much more than it exports. So just to see if we know what's going on, which country has low out degree but exports a significant quantity of petroleum products? In this first visualization, you may have seen Singapore actually have a non-significant out degree. And that's a little bit puzzling because Singapore is a city-state. So where is it getting this oil to export? So what I've done is I have excluded, everything except for crude petroleum, that is the actual oil as opposed to derivative products. And here you can see that Singapore becomes primarily an importer. It has in degree, but it doesn't really have significant out degree. So this illustrates the point that it's when you're talking about centrality, it's very important to know first, what does your network represent? What is its scope? Here, scope is not that much of an issue because we have all countries. However, what exactly do the edges mean? Is it crude oil or is it refined oil? Even little tweaks can make a significant difference. So you just have to know what your network is, and when you're talking to others, you have to honestly represent that as well. So let's put some numbers to it. Let's quantify centrality. And let's switch to an undirected mode in networks for the time being. So in undirected degree, all we're doing is we're counting the number of edges you have. So if it's a friendship graph, it just counts the number of friends. And the basic assumption here is that it doesn't matter how many friends your friends have or anything else. You're just counting the number. That's all that counts. You can normalize this measure by dividing by the maximum number possible for the degree, which is n-1, as we saw just last week. So Here, this node has a normalized centrality of 0.5 because it's connected to 3 of the possible 6 other nodes that are in the network. And although I personally don't normalize centrality degree that often, you will just for my own purposes, I like having the raw count, and especially with large networks, it's, you have a network of 1 million nodes. No one's going to have, all the normalized degree centralities are going to be 0.000, right? Because you're not going to be connected to all the other nodes. That's ridiculous. But a lot of social network analysis software does like to normalize. So I would just like you to get used to these normalized scores. And of course, you can just multiply by n-1 to get the degree back, the number of neighbors for each node. Centrality refers to an individual node, but there is a network-wide measure called centralization that characterizes the entire network, and what it does is it captures the inequality in the distribution of centrality. So it could be the inequality of degree between the nodes. And for this, it doesn't matter that much what particular measure of centralization you use. You could just use the standard deviation in degree. And I have used this, for example, when studying trading networks for commodity futures contracts, right? We just looked at standard deviation in degree, but we also threw in something called the Gini coefficient, which varies from 0 if everyone has the same degree to 1 if one node has, all the degree and all the other nodes have degree 0, which you might see in a star formation. There's also Freeman's general formula for centralization, and what you look at there is you sum over all the nodes, you take the maximum value that you observe in the network, you subtract the centrality of that particular node, and you do this for all the nodes, and then you normalize by this number of pairs, right? And it's just one lower because you get zeros for the node that has the highest centrality. So let's look at a few examples. This is with Freeman centralization. Here, as promised in the star formation, you have perfect centralization. You get 1.0. Here in the line graph, the nodes look pretty similar as far as degree is concerned. We'll see later that using other centrality measures, right, the one that's in the middle might end up being more central, but here all we're doing is counting degree, so all these nodes look pretty similar, giving us a relatively low centralization value. And a similar thing happens for this kind of butterfly network where, again, the nodes have either degree 2 or 3, and it's all very similar. I mentioned these trading networks that I had analyzed. So these are brokers, and they're trading in futures contracts having to do with the S&P 500. And in this case, what I've done is I've sized the nodes by their in degree. So the larger the node appears, the higher its in degree. And I've colored them by out degree. So the larger the out degree, the darker the node. And in any case, you can see that here the network has very high in-centralization because one node really dominates. It has a very high in degree, and most of the others have relatively even in degree and lower in degree. And here on the right, you see that actually all the nodes have relatively even in degree, and no one is really hogging all the end links. So there's an example where we could actually use centralization of the whole network and correlate it with other variables, for example, the returns and volume and other kind of financial properties of the system at that time. But let's return to this question of things that simply counting the number of edges doesn't capture. If we look at this graph, degree may very well capture what's going on. But if we look at this network, right, this node has degree 2, which makes it kind of less important in a degree sense than these two nodes, and about of equal importance as these two nodes. But intuitively we think that this node must be important because everyone here who may want to get in touch with anyone here is going to have to go through this node. So how would one capture that? Similarly here, degree says all of these are equal, but this one, if it wanted to visit any of the other nodes, it would just make 2 hops max, and all the other nodes would potentially have to make 3 or 4 hops if they want to reach some of the individuals in the network. So how do we capture that? Well, let's return to the Stanford Social Web, right? Here again, we have that ORCUD is very central locally. And certainly for my social neighborhood, if any of us wanted to get in touch with the undergrads and so on, maybe ORCUD would be our best choice, and he would kind of be between us and the rest of the network. But overall, his betweenness might not be as high as, for example, some of the other nodes kind of closer in, and his closeness, in a sense that he's not very proximate to the rest of the network, should be low as well. So let's first talk about brokerage. This is where a node lies between other people. Here X plays more of a brokerage role than Y because these two nodes would have to go through X to talk to these two nodes. And there is a bunch of research into this. In particular, Ron Burt at the University of Chicago Business School has studied what advantages individuals who occupy such roles might have. And he's found things such as they're more likely to generate creative ideas. If he studies them within an organizational context, their ideas are more likely to be accepted, they're more likely to receive favorable reviews, and they're more likely to be credited. Now, of course, there's a little bit of an ambiguity. Is it that the person enjoys these advantages because they occupy that position in the network, or did they come to occupy that position because they're a special kind of person who does generate creative ideas, etc., right? And this is a little bit of an ongoing debate. The consensus seems to be that if you put someone incompetent in that position, they're not going to suddenly start to blossom and do really, really well. But if you have a good person in that position, they're in an even better position, or can accomplish even more when they're in the brokerage position. And this goes back to the notion of constraint. And that is that if you are not a broker, you experience constraint in the sense that your contacts are talking to each other, which means that you can't say one thing to one and another thing to another because they're communicating with each other. And so you're constrained in what you might be able to pull off. On the other hand, if you're in this brokerage position, you can turn to one part of your network and say, hey, I would do business only with you. And they have no reason not to believe you, but you could turn around and to the other side of the network that you're kind of bridging, and you can say, oh, you guys are my favorites, and no one would be the wiser. And so this is what's called, like when you're a brokerage position, you actually experience low constraint. So let's look at this measure of betweenness, which is going to capture brokerage. The basic idea is that you're asking how many pairs of individuals in the network would be connected through you on their shortest path to each other. So are you on the shortest path between those other two nodes? And it's possible for there to be multiple short paths. In that case, what you're going to get, so here you're I, and you are on one of the shortest paths between J and K, or one or more of the shortest paths between J and K, but the credit you get is the number of shortest paths that you're on divided by the number of shortest paths that J and K have. And then your betweenness is the sum over all pairs of nodes JK. And you can normalize this. Again, for betweenness, it might make more sense because these values can indeed become very astronomical. But you're just normalizing by the number of pairs of vertices, excluding I itself. So for what fraction of the other nodes are you on the short path? So let's look at a few examples on toy networks. Here, the central node has betweenness 10 because there are 5 times 4 divided by 2, because we don't care about direction, different pairs that go through the central node in order to reach one another. But each one of those nodes individually has betweenness 0 because no one has to go through them to get to anyone else. So let's return to our line graph. And here, naturally, A has 0 betweenness because it's not on the path between any other nodes. B has betweenness 3 because A relies on it to reach every one of the 3 other nodes. C has betweenness 4 because it is on the path between A and B and D and E. Note that in this case, C gets full credit because there are no alternate paths, for example, between B and D. The only way they can reach each other is through C. If we go back to the butterfly network, remember this central node had degree 2. Now it has the highest betweenness. It has betweenness 9 because each of these 3 nodes relies on the center node in order to reach the other 3 nodes in the network. On the other hand, these peripheral nodes here have betweenness 0 because you wouldn't go out of your way in order to reach any of the other nodes. They are on no shortest paths. Let's look at this particular toy network. Here, C and D each have betweenness 1. How do you calculate that? Well, C is on the path from A and B to E, and so is D. So imagine first that D is not there. Well, if that were the case, then C would have betweenness 2 because it's on the path from A to E and on the path from B to E. However, D is on the exact same paths, and so they share credit and they each get betweenness 1. Quiz question: what is the betweenness of node E? Here's an older version of my Facebook network. I've sized the nodes by degree. The larger the size, the higher the degree, and I've colored them by betweenness. The redder the node, the higher the betweenness. And you can see some nodes here that have relatively low degree, but they have high betweenness because they bridge, for example, my undergrad network with my University of Michigan and research network. Another quiz question. Find a node that has high betweenness but low degree. And now find a node that has low betweenness but high degree. What if it's not so important to have so many direct friends? So it doesn't matter whether you want to do this power play where you're brokering between different parts of the network and you want to make sure that they have to go through you. What if instead all you want is that you have easy access to a large part of the network? You want information to reach you in a short number of hops. You want to be able to disseminate the information that you have. And therefore, it's not about brokerage, it's about how far away the rest of the network is from you. For example, in this network, this node has degree 1, but because it's friends with the highest degree node, this means that the number of hops from it to anyone else in the network is only 1 extra hop than it is for the most central node. It in fact has easy access through just that single connection. So we want to capture this notion of a small number of hops. So by definition, the closeness centrality is the sum of the distances between the node in question, I, and all other nodes, j. And you're going to sum these distances and invert them. Now there's a problem in that if your node has multiple connected components, that is, there are nodes in other components than yours, your distance to them is infinite. And when you sum infinity with other things, it means your closeness is actually zero, right? Because here you're inverting. So in order to avoid that, an alternative measure of closeness is to take this inversion inside of the sum. And so you take the inverse of the distance to every other node and you sum those values. So all those nodes and other components, they just contribute zero to your closeness, but you do get credit for having short paths to nodes that are in your same component. And you can normalize this by n-1, the number of other nodes in the network. Here is a toy example where if we look at the closeness of A, it has distance 1 to B, distance 2 to C, 3 to D, 4 to E. We sum those, we divide by n-1, and we invert, getting a closeness of 0.4. Finally, we can also look at our other toy networks, and here again, the middle node has high closeness. The ones right next to it also have relatively high closeness. Here the middle node has high closeness, but the other nodes being directly connected to this hub, that is the spokes, they actually have relatively high closeness as well. They're only 2 hops away from any other node. So looking at this network, can you tell me which node has relatively high degree but low closeness?